really good, or noisy, meaning it will look like a 2 but not really like the input 2. So how do we quantify it to say the reconstruction is pretty decent? Do we examine it visually, or how would you do it through code?
Through pixel values?
Present distance compared
What did we just...
exactly, what information is mutual?
Exactly. If the mutual information is... So if the mutual information is high, that means the architecture is doing a really good job. If the mutual information is poor... So anyway, once again, our idea was, through deconvolutions, through the amoeba algorithm, through the concept of mutual information, we did a smart way of reducing the training data set so that we're not wasting hours and hours to figure out. It has learned, right? So these 4 things we combined in a very, very neat way. So that was one of the PhD dissertations. And so anyway, so I would like you to at least know the concept of mutual information, the concept of the amoeba algorithm. So as we have gone through the example, everybody hopefully knows how to compute the mutual information, right? Okay. Now let me give you the idea of the amoeba algorithm. I used to give this as an assignment. So in fact, the PhD student who did all this work took this course and then knew how to use all of the techniques. Okay, but you guys are already behind on assignments, so I won't make it an assignment, but I'll show you, if you were to do it, how would you do it, okay? So if you again go to the handouts and there's our course, okay, one of the links over here will be related to mutual information. Where did it go? Oh, I'm not in the handout section. Okay, so anyway, you'll see image registration, Nelder-Mead, amoeba method. So I'll briefly go over, okay, actually this is useful also, but I have a better summary of it. Okay, the second link, image registration using mutual information and Nelder-Mead algorithm. Okay, so anyway, we've already looked at the joint PDF formula and how to compute it. Okay, we've already looked at the mutual information formula. So this is the mutual information between 2 images where we sum all the product of joint PDF divided by the individual PDFs and the log and so on. So you guys already know how to compute mutual information, right? Okay, so now the question is, we'll put a negative sign over here. This will become our cost function. And we want to minimize this cost by applying transformation to I2. So the question is, what is the transformation which will result in the lowest negative of the mutual information? And this is where the amoeba algorithms comes into play. Okay, so the amoeba algorithm is fairly straightforward to understand. Okay, so once again, if we have n parameters, so n unknown parameters, okay, we create an n plus 1 dimensional, there there's a technical name for it. Okay, for right now, let me just say n+1 dimensional data, right? So for example, if we have two unknowns that we are trying to optimize, we'll create basically a triangle with 3 data points. Each point is a solution to the problem. So each point is basically 2 values in it. 2 values in it, right? So then we have a concept of the best data point and the worst data point. So let's say based on this data point, right? Suppose our cost is the lowest, so this is our best. Let's pretend this one is worst, and this one is second best. Okay, so then what we try to do is we try to go the opposite of the worst. So there's a step called reflection as an example. So we'll reflect this point so that we move over here. So this worst point becomes over here. Actually, let me show you if I can. Let me show you some pictures in the other handout to easily understand this. So the first link over here. Okay, has some pictures. Okay, so for example, pretend this is the best from cost point of view. This is the second best, they call it good. This is the worst. So then what we do is, based on the location of these, we reflect on the worst. So this is the reflection, okay? Once we reflect, then we try to see, does it improve cost? So does it lower cost? Okay, if it lowers the cost, then this disappears, this appears again. We again compute who's the best now, who's the worst, who's the second best. And so essentially the whole idea is this triangle will move over here, then it will move over here, then it will move over here, then it will move over here. Ultimately, it will find the optimal answer. So, reason they call it amoeba is like a worm. It's like, you know, the worm contracts, expands, it moves until it finds the best solution. So that's the idea. So there's a double reflection over here. So let's say we reflect it, and this becomes better than the best. Okay, maybe we should do double reflection over here. If already we know in this direction the solution is improving, maybe this will be even a better solution. Okay, so if you take a look at the picture below, okay, so this is basically double reflection. Okay, D and D. So the technical term for this is expansion. Okay. So if the expansion did not turn out better than the reflection, then we'll just use this as our next shifting of the shape. So the shape will now become like this in the next iteration. Okay. What if even the reflection doesn't give us better result? Then the opposite is contraction. Then we go move it in this direction. So in short, we have reflection, expansion, which is essentially double reflection. And again, both of these are on the worst point. Okay, and then we have contraction, like I said, which goes opposite. We create the center of gravity and we move it in that direction. Okay, and there's one more step over here. So basically this is what we do. Okay, so I have two handouts just in case later on you wanted to understand this algorithm better. Okay, one was the copy of a chapter on numerical optimization called Nelder-Mead. So it does a good explanation of it, but in my opinion, the final algorithm they present is not in a good algorithmic form. So I basically converted this to my own way of, and this is the first link over, sorry, the second link over here. Image registration using mutual information and Nelder-Mead algorithm. So if I go to this one, okay, so first was just the theory of mutual information, which we already have a good handle through the joint PDFs. You guys already know the transformation, right? Okay. So in the handout that I've given, remember our transformation usually goes like S cosine theta, S cosine theta, S sine theta, something minus S sine theta. Okay, so if we call this A, we call this B, we call this negative B and A. Okay, so this was under the condition that there is no shear. So if there's no shear, then B and minus, these two are exactly the same and the diagonal is the, except for the negative sign. Okay, but if we wanted to completely generalize it so that one could be a little bit sheared version of the other image, then our unknowns become four unknowns, A, B, C, D. So then, so if we wanted to make it completely flexible, no restriction, then this will be C, this will be D. Okay, so in this case, our number of unknowns will be 6. Everybody agrees? Okay, so that means in our amoeba algorithm, how many? 1, 2, 3, 4, 5. We'll create 7 points. Okay, each will be a potential solution to the problem, meaning each will have A, B, C, D, T1, T2. Okay, so F, let's pretend, is the cost associated with it. So based on the ABCD, as we compared to the mutual information with the reference image, so then we basically sort these. Okay, so this will be the best or the worst. If the mutual information is low, this will be the worst, this will be the best, right? So then we can have a best, second best, and worst. Then, like I said, we'll do a reflection on the worst. If it produces better answer, we'll do an expansion, which is double reflection, and so on, right? So the final algorithm, in 2 more minutes, looks like this.
But aren't we trying to optimize it?
Yeah.
With a minus sign in front, so the
Correct.
smallest one will be the best one?
When I wrote it over here, if there's a negative sign, you're right, then this will be the best one, yeah. But the point is basically sorted by cost, and then you know. So anyway, this is what the algorithm looks like. Okay. Initialize the simplex vertices. So simplex is basically the shape I was looking for, the technical name for it. Okay, if we have 2 unknowns, then our simplex will be a triangle. And if it is, in our case, we had 6 unknowns to solve for, so it will be a 7-dimensional simplex. Okay, so we'll initialize. What I mean is A, B, C, D, T1, T2 to reasonable values. Meaning it won't make sense to put 1,000 for A and 10,000 for C. So you'll pick, for example, A, B, C, D might be between 0 to 1, T1, T2. If we know, maximum shift could be 100 pixels, it could be 0 to 100 for T1, T2. So based on whatever prior information we have, we'll randomly create, in our case, 7 points, 7 vertices, each with 6 values. Okay, then we basically repeat it, compute the cost. Okay, we sort them by the cost. Okay, then best, in this case, I'm assumed to be Z1, and let's see. So yeah, the lower cost, because we have a negative, this will be our best, and this will be our worst. Okay, so anyway, so we compute the cost, set the best to Z1, worst to the last one, and in this case, rather than picking a second best, I was picking the second worst. There are variations of this algorithm where we pick second best instead of the second worst, but this particular algorithm operates on the second worst. Okay, then this is the formula. So this is a simple vector arithmetic because all of these are basically 6 by 1 vectors. So we try to do, first we compute the center of all the vertices, which is like the mean of all the vectors, all the 7 points. Then reflections formula is C plus C minus W. W is the worst vector. And if the cost becomes lower than so anyway, then we basically replace W with R. And then we try the expansion. And if the cost is still lower, we replace the expanded node, W with the expanded node, and continue on. And like I said, then there's a contraction at if neither one of them is improving, so then we do the opposite. So these are the vector, again, operations, and we basically keep repeating this. In the end, whatever is our best, so the amoeba will keep moving, and in the end, whatever is the best will be our final solution. So usually this works pretty fast, and not too many, maybe 30, 40 iterations, it's able to find the answer. Okay, if you were to build it actually, like I said, I used to give this as an assignment. So here's the partial code for computing the actual code for the mutual information. So the first one is computing the PDF, right, for one image. And all you can see is it basically incrementing the pixel value if it finds it again, if by 1. So pretty straightforward. So this will compute the PDF, for example, P of A. Okay, this will compute the joint PDF. So this is the actual code based on a given transformation. So if we apply transformation to T2, after applying the transformation, what will be the joint PDF? So again, you can easily see this is pretty straightforward. And lastly, what is the mutual information? Okay. So exact same formula that I showed you over there. Okay, so later on, if you run into, especially I came across a very recent deep learning research paper where they were using mutual information to create a generative model. So at least now you have an idea of it so that you can understand, if you run into this, what it is. Okay. All right. If you are able to, today in the deep learning class, I'll be going over TensorFlow. As well as variational autoencoders, which are needed in vision as well. So not mandatory, but if you are able to follow that as well, it will be good for you.